later. So hopefully you're seeing my screen and you're hearing my voice. And we're looking at the Lewis structure quiz. The first one is SOCl2, which is thionyl chloride. So the first thing we want to do is count up the number of valence electrons. There are 6 on sulfur, 6 more on oxygen, 2 times 7, which chlorine has 7, so that's a total of 26 electrons. We want to make sure our structure has 26 total electrons. Sulfur is the least electronegative element, right? It's below oxygen and to the left of chlorine. So sulfur is the central atom. And we're going to make a single bond to each of the other 3 atoms, using up 6 of the electrons, which leaves us with 20. 18 of those electrons can be used by filling the octet on the outer atoms. But that's 24 electrons total. The remaining 2 are going to go in the central atom. As soon as you notice that it's not a multiple of 8, 26 electrons is not a multiple of 8, you know that there are going to be some electrons on the central atom. So this is a legitimate resonance structure. It's not bad. It has filled octets on every atom, but it does have formal charge because oxygen now has 7 electrons to its name, the 6 electrons that are part of the lone pair, plus it gets to take half of this bonding pair with it when it leaves. So that's 7 electrons. It only brought 6 as the valence, so it has an extra electron. It's got a negative formal charge. Sulfur has a formal charge because it gets to take these 2 electrons and 1 each of the bond, so that's only 5, and it brought 6. So the sulfur has a positive formal charge. So that's probably not going to be the best Lewis structure because we can likely expand the octet on sulfur and avoid formal charge. So the way to do that would be to just push a pair of electrons from the oxygen in to form a sulfur-oxygen double bond. And we leave the single bonds to chlorine. Chlorine really wants to have 3 lone pairs and 1 bond. That's the optimum situation. The lone pair on the central sulfur is still there. This one's going to be the best structure because although it expands the octet on sulfur, it avoids formal charge. And if you avoid formal charge, that's usually better than the one that has formal charge. The other possible way of solving the formal charge problem on sulfur by giving it an extra electron would be to move one of the lone pairs from the chlorine. So there are also 2 equivalent resonance structures that have the single bond to oxygen still, but a double bond to one of the 2 chlorines. Still the lone pair on sulfur. So oxygen still has a negative formal charge because it still has 7 electrons, but the positive formal charge is now on the chlorine. The chlorine takes 6 electrons with it, 4 lone pairs plus 2 from the bonds. And I asked for 3, but there are 2 equivalent resonance structures because there's no difference between the 2 chlorines. Right? Both of these lower resonance structures, although they're minor contributors, are possible. It's just a matter of which chlorine has the positive formal charge. So the best structure is the structure that has no formal charge at all. The second best would be this one, because at least when it has the positive and negative formal charge, the negative charge is on the most electronegative element and the positive charge is on the least electronegative element. And then these would be minor contributors because the positive charge is not on the least electronegative element. So hopefully that one went well. If you have any questions, by the way, feel free to break in. I don't mind being interrupted. This is, I can't actually see you, so if you're waving your hand, I'm not seeing it. The second example is Ch3 Nco. So 4 electrons on the carbon plus 3. 4 electrons on the carbon plus 3 times 1 for the hydrogen plus 5 for the nitrogen plus 4 for the other carbon plus 6 for the oxygen. So 10, 15, 18, 22 electrons total. And we're told that we're going to connect these in a skeleton that looks like that, where we have carbon, nitrogen, carbon, oxygen. Right? That's because the condensed formula is Ch3 Nco instead of Ch3 OCN or some other example. The 3 hydrogens here are attached to the carbon to their left, so we can put the rest of the framework together. We've used 12 electrons, so 10 remain, and we would normally put 6 of them on the oxygen and the remaining 4 on the nitrogen. So that's a structure that has the right number of valence electrons and the right order of atom connectivity, but carbon has an unfilled octet, so it's not very happy. The way we're going to solve that problem is we're going to make multiple bonds to the carbon. We're going to have 4 total bonds to the carbon. So there are a bunch of different ways you could do that, depending on whether you take lone pairs from nitrogen to make a triple bond here, or lone pairs from oxygen to make a triple bond there, or some from nitrogen and some from oxygen. So the possible ways of arranging that are triple bond on the nitrogen side, single bond on the oxygen side, or triple bond on the oxygen side, single bond on the nitrogen side, or double bond on each side. All of those structures will, that's nitrogen. All of those structures will satisfy the octet rule on carbon, still satisfy the octet rule on the nitrogen and the oxygen. So now for these 3 structures, to determine which one's the best contributor, we need to use formal charge. Oxygen with a single bond to it like that and 3 lone pairs will always have a -1 formal charge. Nitrogen, if it has 4 bonds and no lone pairs, always has a positive formal charge. Oxygen here takes 5 electrons with it, so there's a positive formal charge on that one. Carbon's happy, but the nitrogen here now actually gets to take 6 electrons with it, right? That's not happy. That's got a negative formal charge. So the structure on the left here is better than the structure on the right because it has formal charge separation in both cases, but the negative on the more electronegative element is the best. But the best structure is the one that you have here, where there's no formal charge. Right, because nitrogen now takes 5 electrons with it, which is the valence. Oxygen takes 6 electrons with it, which is its valence. Carbon is happy. So we can avoid formal charge by putting double bonds on both sides. The second best would be this one, and the one that has the negative charge on the nitrogen, which is less electronegative than the oxygen, would be the minor contributor. So that one was right out of the video. Lithionyl chloride was right out of the quiz. So now we move on, and we've got an attempt to turn this into a bond line formula. One of the first things I would do is count the carbons in the main chain. So the CH3 is 1, CH2 is 2. This CH3 group is a branch off there, so we don't count it. That CH2 is 4, 5. Again, this CH2OH is a branch. 6, 7. One of the oxygens is going to be 8, 9, 10. So the main chain has 10 atoms in it. I'm going to start by drawing a zigzag line that has 10 points and 9 bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that looks like it's got 10. Right, so that's the CH3. This is the CH2. This is the CH, and it has a CH3 branch off it. So I'm going to put the methyl group there. Then a CH2, then a CH, and this CH2OH group is off that. So I'm going to draw the CH2 as a point and then put the OH. We always label the oxygens. CH2 here. This carbon has a double bonded oxygen to it. And then atom number 8 is in fact an oxygen. And then we've got a CH2 and a CH3. So the bond line formula looks like that, or if you started your chain drawing the other way, you would have had it looking like this. where we've got a main chain here, and then these two substituents. We've got a methyl group and we've got what's called a hydroxy methyl group. This is an ester functional group here. And over here we also have an alcohol functional group, so it's a difunctional compound. And in a minute we'll actually talk about how to name that compound. And then now we're going the other way. Got a structure going to a condensed formula. You'll probably recognize that as the benzene ring. That's going to be abbreviated C6H5, or if you prefer pH, although the C6H5 would be better in the condensed formula. This is a methyl group as a substituent, so there's going to be in parentheses a CH3 for that. There's a chlorine here, right, as a substituent, and then it's an aldehyde functional group over here. And I'm going to label that as CHO. That's what we use for an aldehyde. So C6H5, then there's a CH2 group, then there's a CH that has off it a CH3, then there's a CH that has off it a Cl, then there's a CH2, and then we have our aldehyde CHO. So C6H5, CH2, CH parentheses CH3, CH parentheses Cl, CH2, CHO would be the condensed form. And we can talk about how to name that as well. Are there any questions? Yeah, go ahead.
For the last one, does it have to be CHO or can it be COH? Is that going to change how it...
Yes, it has to be CHO. Because if it's COH, you're saying that the hydrogen is attached to the oxygen. The hydrogen is attached to whatever heavy element is to its left. So if you wrote it as COH, what you'd be telling me the structure looked like is the CH2 group here, and then C, and then OH, and this carbon would have an unfilled octet. Right? So you don't want to do it that way. Aldehyde is CHO. Carboxylic acid is COOH, because the hydrogen in the carboxylic acid is actually attached to an oxygen, not to the carbon. Any other questions on the quiz? I think I said it's 24 points, so it's basically 2 points for each resonance structure, 1 point for choosing the right one, and 2 points for telling me why it's the right one. So you've got 18 there, and then the line to condensed and condensed to line is 3 points each. So I'll scan these, I'll post them. But let's talk about how to name these compounds. Actually, we'll start here. So I don't know how many of you have actually spent some time on naming, so maybe I should review kind of the rules. So in naming compounds, the first thing you always want to do is identify the longest chain. So, for example, if I had something like this, right, the longest chain would be this way. Step 2 is to number the chain so that the first substituent gets the lowest possible number. So in this case, I would get to this group sooner if I started by numbering carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Right, that would be better than 1, 2, 3, 4, 5, 6, 7. So I'd number it in this direction. Right. The longest chain is 12 carbons, which means it's a dodecane. And I've numbered it so that the first substituent gets the lowest number. The substituent is at carbon 6. This group is an ethyl group. So in this particular case, this molecule would be 6-ethyl dodecane. So when you're numbering the chain so the first substituent gets the lowest group, you give preference to a larger number of small substituents instead of a smaller number of large substituents. So if you can avoid branched substituents, that's great. If there's a tie, it goes alphabetical. And when you're naming it, you also go alphabetical. And then when you have functional groups in there, there's an order of priority where the most oxygenated carbon takes precedence. So the carboxylic acid is preferred over the aldehyde or ketone, which is in turn preferred over an alcohol, which is preferred over an alkyne, which is preferred over an alkene, and then the last priority are the alkyl halides or alkyl substituents. So that's kind of the rules that you want to follow. Find the longest chain, number it so that the first substituent gets the lowest number. If there's a choice, you'd prefer to have lots of small substituents instead of one or two really complicated substituents. Alphabetical when naming, right? And then the functional group order of priority. If you have a carboxylic acid, that's carbon 1 automatically. If you have an aldehyde, right, and no carboxylic acid, then the aldehyde becomes carbon 1. When you have an alcohol, even if you take longer to get to the alcohol group than you would to get to an alkyl substituent, you're naming it as a parent alcohol. So you want the lowest number on the OH group, not on the alkyl substituent. So let's try to apply those rules to naming the two compounds that were part of the quiz. So let's take a look at this one first. Do that so it's actually straight. So how many carbons are in the longest chain? And don't count the C6H5 group as part of the chain. That is going to be a phenyl substituent. Five. So the longest chain is 5. We want to number it. Which carbon do we want to assign carbon number 1?
With the aldehyde on the end.
Yep, so the aldehyde is number 1. Instead of this being number 1, the aldehyde takes priority. There's no carboxylic acid group, so that's carbon 1, and carbon 2, carbon 3, carbon 4, and carbon 5. Okay. So you can see that there actually are 3 things off that chain. But since it's 5 carbon, the parent is pent. And because it's an aldehyde, we take off the E and put an AL ending on it. So it's a pentanal. If it's an alcohol, it's going to be a pentanol, an OL ending. So we're going to name this as a pentanal, and now we have to look at the substituents. Right? There's a phenyl substituent, there's a methyl substituent, and there's a chloro substituent. The phenyl group is on carbon 5, the methyl group is on carbon 4, and the chloro is on carbon 3. So what order do we want to put them in when we name it?
Alphabetical. Start with the chloro, and then wow, I can't do the alphabet this morning. The methyl, and then the phenyl group.
Right. So in order of priority, chloro C comes before M comes before P. So we actually want to name it the other way. So it's going to be 3 chloro, 4 methyl, 5 phenyl, pentanal. Notice that when we have the numbers in there, we separate the numbers from the letters with dashes. If you have 2 numbers, then you separate the 2 numbers by commas. Right? So actually, if I wanted to draw this molecule so that it kind of went in order, I'd want to flip it around and draw it the other way. So I would draw it like this. And then I could be numbering from left to right rather than from right to left. Doesn't really matter which direction you number it in. So let's take a look at the other one. So where's the longest chain in this one? And when you're counting the longest chain in this one, don't count that part, because it's separated from the rest of the molecule by this oxygen.
Five.
5 is not the answer. There are more than 5.
There are 7, and your first one would be next to the 2 oxygens.
So there are 7. This is a derivative of a carboxylic acid. It's an ester. So what it is, it's a combination, right, of carboxylic acid and an alcohol, where what we've done is we've taken away the elements of water and then connected the bond up. So it's named as if it were carboxylic acid. And we number it this way. And then we name this piece separate. This is an ethyl group. And this is a heptanoic acid. So it's going to be an ethyl heptanoate. Right? It would be heptanoic acid. And what we do is we take off the ic acid part and replace it with ATE when you have an ester. So heptanoic acid becomes heptanoate. And then the ethyl group is there, it's an ethyl heptanoate. So now we have to look at the substituents. And we have a methyl group on the 5 position. And we have a hydroxymethyl group on the 3 position. So which one of those would come first? H before M or M before H? Who's got their alphabet down today?
H.
H first. So this would be 3 hydroxymethyl. And since it's a complex substituent, we put it in parentheses. Five methyl heptanoate. And the ethyl part still comes out front. So the full name is ethyl 3-hydroxymethyl 5-methyl heptanoate. Right. Make sense?
Does the ethyl go in there anywhere, or do we just drop it?
The ethyl goes here, right?
Oh, in the front?
The parent was the parent compound was an ethyl heptanoate, and then we just had to figure out where to put the substituents, and I unfortunately didn't leave myself enough space to write the ethyl in front of it. I should have.
Okay, would there be a dash between the ethyl and the 3?
Space.
Just space? Okay.
Because it's a separate group.
Okay.
So the full name, if I'd left myself enough space, would be like that. And here's a space.
Thank you.
Okay. So there's half an hour left in the class. So what I would suggest you do is, I'm going to stop this recording here.